Oh yeah, thank you for recording.
Okay.
I forgot about it.
So remember the theorem.
Mm-hmm.
Only the theorem says that the integral around a closed curve in a simply connected region, it's only zero if fz is analytic inside that region, right?
Yes, yes.
So when we go down to this function f of z,
it's not analytic at point 2.
Yeah, when you look at this region, the function is analytic. So the integral is going to be 0. For this region, the function is analytic, the integral is going to be 0. But along this curve, it's not analytic at the point 2.
2. Yes,
and so
I agree.
The integral cannot be 0 at that point. Yeah.
Let me make a quick note, okay?
Yeah.
If function of the is not analytic at some point inside of the curve, some point inside of the curve, it means that the integral of the function is not equal to 0. Okay.
Yeah.
Okay.
So if that integral is not equal to 0, what is it?
Let's find it.
Now you need to find it.
Yes.
And I believe that is what we are about to do. So you have the integral around a closed curve C, 1 over z minus z naught dz. So that curve is a closed circle of radius delta.
Oh, delta, sorry.
About the point z equals z naught.
Okay.
So if it's a closed circle, then we can only integrate
from 0 to 2 pi.
0 to 2 pi.
Okay.
1 divided by delta ei theta. So let's see how this came to be.
G equals z naught plus delta ei theta. Uh, 2p, it's understandable from 0 to 2p. Sigma, it's just a vector, it's radius. I mean delta, sorry. Delta is a radius. Theta is an angle. G dot plus delta times E in power of I theta. We need to integrate the curve, the contour.
Yeah. And remember ei theta equals?
Ei theta, it's this French guy formula.
Yeah. Cos theta plus I sine theta.
Yes.
I'm trying to ask myself why. So I can see that this, if this is theta, if that's theta, then cos theta is going to be this. I mean, sine theta is going to be this side divided by that side. Let me call that side x. So the sine of theta is going to be this side x divided by delta.
Delta.
So x becomes
sinus theta,
delta sine theta.
sine theta.
And then this length
Cos. Let's find cos.
is
Cos
going
theta
to be
equal z naught divided to delta
delta cos theta.
theta.
And remember, z is the point, x plus iy.
Iy.
So z is going to be the point
Delta
sine
sin
theta
sine theta
plus I
delta I cosinus.
cos theta. So which is going to be delta.
But it's not a formula. It's sinus theta plus I cosinus theta. It should be inverse.
Oh, this is the y. Going up is the y. And this is the x. This is the point. Yeah, it's, yeah.
Yes,
This is the y,
right.
this is the x.
Yes.
So this will be
sigma I,
this will
delta
be cos theta.
Or cos theta, yeah. You can.
Let me just do it again.
Okay, now I see you.
So so this point is the z. Okay. And going up is y, and then going straight is x, and the z is going to be x plus iy. So z equals x plus iy. But x is in relationship to theta. X over delta is cosine theta. So x is going to be delta cosine theta. And then y is going to be delta sine theta. So the point z becomes delta cos theta plus I delta sine theta. If you factor out the delta, you get z equals delta cos theta plus I sine theta, which will become delta E I theta. So that's how we are getting. So we are getting z from this point.
It's not z equals, it I theta equals delta cosinus theta plus I.
What?
Oh, right. Sorry, my bad.
Yeah. Okay. So this point is going to be delta EI theta away from Z naught. You can see that. It's delta EI theta away from Z naught. And that's why we are saying that the point Z is going to be equal to Z naught plus delta EI theta. Yeah. Okay. Because you can see this is the origin. So actually here I should have said that Z is going to be equal to, already we have Z naught plus X plus IY.
Plus IY.
So it's Z naught plus this X plus the IY. So at least this point is clear how Z equals Z naught plus delta EI theta.
Yes.
And then
so
Z minus, yeah.
Yeah, go ahead. I'm just writing.
So Z minus Z naught becomes equal to delta E I theta. dz becomes equal to delta I E I theta d theta. So this is elementary calculus. So we have transformed.
Why it's happened? Why it goes down? I mean, like dz, I understand that dz it's like it's a operation of z minus z naught.
Yeah, so z minus z naught. If you differentiate this becomes dz, the z naught becomes 0. And then this is delta. And then you're going to differentiate this with respect to I theta. It becomes ei theta. But now you do the chain rule, differentiate the I theta with respect to theta. It becomes I, you multiply. So delta I ei theta d theta.
Okay.
So this contour integral has been transformed to integral from 0 to 2 pi 1 divided by z minus z naught is delta.
Yes.
E I theta.
I theta.
And then
times
dz is delta E I theta multiplied by I d theta, right?
D theta, yes.
So the delta cancels out with the delta. EI theta cancels out with EI theta. So we only have integral 0 to 2 pi 1 times I is I d theta.
Okay. Could you remind me, how can I count the integrals? I mean, like, how can I solve it? I don't remember.
Integral?
Yes.
Power rule. So the integral of x dx, x to the power of n dx, is usually given by, so it's the opposite of differentiation.
Oh, okay.
You remember in differentiation, we were subtracting 1 from n, so you add n plus 1. And then instead of multiplying, like in differentiation, you divide by n plus 1.
Yes. Yeah. Oh, we here divide.
Yeah. So that is the power rule for integration.
What's a c?
Just a constant. It's going to be a constant. Yeah.
Okay. So in this case, it will be.
So 1 is a constant. It can come out of the integral sign. So this is simply I 0 to 2 pi, and then you're integrating 1 d theta. Let me write 1 power 1 d theta. It's actually 1 is x power 0, right? It's going to be theta power 0 d theta, right?
Yes.
Because 1 is any number powered by 0. So if we use this rule, it's going to be I, and then you do 0 plus 1, theta, 0 plus 1 divided by 0 plus 1. Okay?
Okay.
It's just going to be I theta. So it's going to be.
I thought that we need to n plus 1. N, I thought it's the upper limit, no? And it's not upper limit.
N is the power. N is the power.
Okay,
yeah.
Okay.
So in this case, the power is 0. Remember, this is the integral.
Yes, yes.
Yeah. Remember, this is the integral.
Sorry, go ahead.
Okay.
Sorry
for interruption. So n is the power, right?
Okay.
So the answer is going to be, you have the I on the outside, yes. And then it's 0. I mean, theta powered by 0 plus 1. So it's going to be theta power 1, and then divide by 1. So you get I integral theta, and then you are integrating from 0 to 2 pi. So replace theta with 2 pi, you get 2 pi I, minus replace theta with 0, you get 0 I. So the result becomes 2 pi I.
Okay.
So that integral around that curve is going to be 2 pi I.
Okay.
Yeah. So this is something you should always remember, that the contour integral around curve, the contour integral of a function 1 over z minus z naught dz will always be equal to 2 pi I.
It does not depend, you're reading this one, right? It does not depend on the radius.
Yeah. So the answer will not depend on the size of the radius. The radius can be small as we want, or it can be as large as you want.
Because it's cancelled out.
Yeah. And then if you don't have one, if you have any constant, which we are calling C naught instead of 1, then that integral will be the same as C naught multiplied by the integral of 1 over z minus z naught dz. It's going to be 2 pi I multiplied by that constant C naught.
It means that we just can take it out of the integral.
Yeah.
Okay, got it.
So we move on to Cauchy integral formula. So if the function f of z is an analytic function on and in the interior of a closed curve, and z naught is a point in the interior of the contour, then f of z naught is going to be equal to 1 over 2 pi I integral of f of z divided by z minus z naught dz.
I didn't get this one. If our function is an analytic function, in the point of the contour zone. I mean, we need to, it means that we need to use this method everywhere in the curve if we have z naught inside of the contour, in the interior side. That is was it. They trying to say that?
Let's see.
Okay, a little bit unclear.
I think they are trying to bring about, I think somewhere along the way, we are going to talk about residues somewhere along the way. Okay, so okay, so this is a statement. It's a formula, Cauchy integral formula. It says that if f of z is an analytic function on and in the interior of a closed curve, and z naught is a point in that interior of the contour, then f of z naught will be given by this function. So it says that if you pick any point inside that contour,
okay,
then this function can give you the value f, the function value at that point, z naught. Let's try to find the connection. First, we know that
the inside of the curve where the function is not analytic, this integral does not equals 0. Then it means that we need to solve it if the function is not analytic. But in this case, in the Cauchy integral formula, they said that the function is an analytic.
Yeah, it's analytic at every point.
And at every point, yes. on the curve and inside of the curve,
Yeah.
but they have a point z naught inside of the curve where the function is not analytic. Then we use this formula, right? Did I understand it?
No, the function,
not? No.
it's analytic.
Sorry.
The function is still an analytic at z naught.
But it should be equal 0 because no, we were not finding, but the function should be equal 0 because the contour is closed and it's simple and the function is analytic.
Yeah, and okay, I see what you're saying. The integral of f of z dz is going to be 0. I agree.
Okay, yeah.
I agree. But realize this is not the integral of f of z dz. There is something we have introduced down there so that it doesn't become a 0.
Okay. Now I got it.
Yeah.
Now it's clear.
Yeah. I'm trying to prove it.
Yes, I see. I'm thinking about it as well.
Yeah, I'm trying to prove it from the other theorem about 2 pi I. So what do we know? We know that integral 1 over z minus z naught dz
it's 2 pi
is 2 pi I, right?
Yes. This is an integral of the contour, but now we're looking for integral at a point.
Yeah.
Maybe this is a reason why we need to times integral of the contour times to the integral of the point. But we can't do it. I mean, like, we can't use integrals to the only one point. Integrals have a like limits from a to okay.
Okay, I'm trying to prove it, but I think we can just use it as it is. But I can see 2 pi I is going to be the integral of 1 over z minus z naught.
Okay.
Okay, yeah, let's just use the formula as it is.
So fz naught.
So the formula says that if you want to find f of z naught, then you have to do 1 over 2 pi I contour integral of f of z over z minus z naught dz. Yeah. So the limit z to z naught power n g of z as z tends to z naught equals f of z naught. It's going to be a pole of order 1.
Why we're talking now about the limit?
Remember how we defined simple poles and stuff like that?
We are finding the limit.
We were for example, so remember how we were defining poles of order 1, poles of order 2, etc.
Where when z equals 1, we will find the pole of order 1.
It was the power.
The power.
Yeah. So the definition was, if you do the limit as z tends to z naught, z minus z naught powered by n, and then you have a function of z, your answer should be a constant. If you get a constant answer whenever you do the limit as z tends to z naught, z minus z naught power n g of z, if the answer is constant, then z naught becomes a pole of order n. Remember that definition? about poles of order n, and then we said that if n equals 1, then it's a simple pole. Yeah. So that is the formula they brought in. That is what they used to come up with Cauchy integral formula. That is what was used. So the C, the constant C, becomes your f of z naught. The constant C becomes your f of z naught. Yeah.
Okay.
So by the other theorem about, this theorem is the one, this Cauchy's theorem is the one that said that if f is analytic, then the integral will be 0, right?
Yes, right, I agree.
So this integral along the contour plus the integral from A to B plus the integral
of G
along the contour G minus
-8.
this integral.
The same integral.
Yeah,
as
they're all going to be 0.
Okay, I agree. So C where equals -G, and it equals contour of G. Oh, okay.
So if you integrate it along the smaller curve, it's going to be negative the integral along the G curve.
It depends on direction.
Yeah.
But the same curve and another direction, it will be another sign different. I mean, plus and minus.
Yeah. Okay, so this integral, this one goes to 0. But this one does not go to 0.
I didn't understand why they use it. Why they divided to, it's the same integral with the same direction. It's divided to 2 different integrals with the same, it's the same contour, absolutely, it's G. Oh, it means maybe it's equal because f of z minus f of z naught will be analytic. F of z naught is not analytic.
Yeah.
Okay.
This one will not be analytic.
Epsilon, where is epsilon? Given any epsilon, we can find as delta. Epsilon naught, it means the center of the curve of the contour G. Okay, it's reasonable. Given any epsilon greater than 0, but we also can find if it's negative.
No,
if it's just
it has to be. It has to be positive.
But our contour can locate it in the third quadrant.
You know, epsilon is the distance.
Oh, epsilon is the distance. It's not. It's not
the
point.
distance. It's the distance between f of z and f of z naught.
Okay.
Yeah, it has to be positive.
Okay, in this case, yes. Okay, so that the okay. Okay, and so it means the distance equals the radius
between f of z and f of z naught.
Yes, it means that
Delta,
the
delta is
f of
delta is the one that equals the radius.
okay.
Delta is the
But
distance between z and z naught.
but epsilon is not radius.
No,
It can be any point in like in the inside of the curve. Any
epsilon
point
is not
inside.
epsilon is not even inside the curve.
Oh, epsilon is not.
It's the distance between the functions f of z minus f of z naught. You know, f of z.
But epsilon equals, does it equal to delta?
No, you know, f
No.
of z and f of z naught, these are not inside the curve.
Why?
Whenever you draw the curve on the plane, maybe you could have a z there, you could have a
Yes.
z naught there. These are inside the
Yes.
curve, right?
Yes.
But the function kicks them out of the curve into some other imaginary space out there.
Okay.
So we are talking about the distance between the function. You know, let's say you are dealing with real numbers. You see, let's say you have 1, 2, 3, 4, and then you have a function f of x. What does it do? It picks these numbers and pulls them up to somewhere. So you see, this function is going to pull z outside the plane. So if this is my plane, the function of z is somewhere in the air. It's somewhere between me and this laptop.
Okay.
Yeah. So the distance between f of z and f of z naught is the one we are calling epsilon. And then the distance between these two is the one we are calling delta.
Okay.
Yeah. So there they are showing that the function f of z is continuous using the epsilon delta notation of continuity. And then what are they doing at this point? Oh, this is how they are proving the theorem we had above. And they just proved it. Okay. So all that was proving the Cauchy integral formula. That was proof of
it was here, Cauchy integral formula.
Yeah. Let's try to go through it again. So this is A.
Which one? Okay.
Where is B?
B, it's on the curve of the G.
Where? Has he written it?
Do you see two arrows below the A? Two arrows which just go up and down. So B, it's on another side of the arrows.
Oh,
it's right here. Yeah. Yes. B is right here. That's why it's cancel out the integral of A to B and integral from B to A. There's the same of the he's making the same the whole like complicated curve.
Yeah, I see. Integral of A to B cancels out with integral from B to A. And so the contour integral of f of z dz over z minus z naught 0 equals
it's a huge one, contour C. It's a big one, contour.
Yeah.
And G is a small contour.
Yeah. So both of them will be 0. Okay.
Supposed to be. The summation of this one.
Yeah.
It says that they equal. Well, yeah, you can see below that they equal. I mean, like only the sign is different because the direction is different, but they are both the same.
Yeah, I can see that. So this is C counterclockwise. it's equal to negative g counterclockwise, but negative g
No,
clockwise.
Clockwise, yes.
And then it's equal to integrating along g counterclockwise.
Yes.
Okay,
Yes.
that's clear to me.
To me too.
And then what's happening here? So integral of g counterclockwise, f of z over z minus z naught dz, it's going to be integral of z, integral along g counterclockwise, f of z minus f of z naught over z minus z naught dz. Why does it go to 0?
Because we're subtracting fz. It's not analytic function. Oh, I mean, it's analytic function. So fz naught, f of z naught is not analytic. That's why we need to solve it. When I think so. Maybe I'm wrong. Fz minus fz naught, it's analytic function. That's why we don't need to solve this integral. It will be equal 0.
Okay.
I only think so. Maybe it's not correct.
Then I choose to believe you.
Okay.
I choose to believe you, but it goes to 0. Let's say it goes to 0.
Okay, we will see. You said they're gonna prove it below.
It's actually part of the proof.
Okay.
This is the definition of a derivative. F of z minus f of z naught divided by z minus z naught. That is the definition of a derivative, right?
I don't remember this definition of derivative.
So it's analytic. How do we define a derivative? Change in y divided by change in x, right?
Oh, yeah.
Which you could also say it's the change in the function divided by the change in the variable. You see?
Okay.
So if you do f of z minus f of z naught,
F of z naught
divided by z minus z naught, that is in itself a derivative.
Okay. So it means it's equal 0. I need to remember.
So it's analytic. You are right. It's analytic. I was convincing myself. It's analytic because this is the definition of a derivative in itself. So that goes to 0. And so integral f of z, let me just write this. So integral f of z divided by z minus z naught dz becomes equal to integral. So this is g counterclockwise. So this will be equal to the integral f of z naught over z minus z naught dz. The two integrals are equal.
Okay, I agree. What we just discussed, I mean, above.
Yeah. So you bring in the epsilon and then the delta. So you let epsilon approach 0 and delta approach 0. So,
okay.
So this limit will be less than this limit.
Could you okay. Okay, I see what you're talking about.
Which will be less than epsilon over delta dz, which will be epsilon over delta, that integral dz.
Because epsilon and delta, it's constant. They're constants.
Yeah. Which will be epsilon over delta 2 pi. 2
but
pi.
I don't remember how to find limits of the integrals.
It's the same thing.
Same thing.
It's not different. You see here we have that f of z minus f of z naught is less than epsilon, right?
Yes, yes.
So we already have f of z minus f of z naught must be less than the modulus of f of z minus f of z naught. right?
Less or equal. Okay, yes, I agree.
So we are
Because-
just simplifying it. So less or equal. So we have simplified it up to this point.
Okay.
Okay. So limit epsilon is approaching 0, delta is approaching 0, and this is epsilon over delta dz, that integral. Epsilon over delta is already a constant. So this will be limit epsilon approaching 0, delta approaching 0, epsilon over delta integral dz. We already saw that the integral of dz is going to be 2 pi. I think we saw in, I think we saw it somewhere here. Integral theta to 2 pi will be 2 pi.
Okay.
Yeah. So this again simplifies to the limit. Epsilon is approaching 0, delta is approaching 0, epsilon divided by delta. And then you have 2 pi. Where is delta coming from? 2 pi times delta. I really don't know where the delta comes from. But once it cancels out with the other delta, when epsilon approaches 0, this limit, it approaches 0. So in short, they are saying that this function will be less than or equal to,
Sigma.
to
Delta.
0. It will be less than or equal to sigma, but because sigma is approaching 0, it will be less than or equal to 0. Yep. So what just happened?
Why it says again 2 pi I? It's from the formula above.
Why it says 2 pi I?
It says the integral of the contour G as delta approach 0 does not depend on delta. So f of z is a constant. F of z not it's constant, right?
Yeah.
That's why we're taking it out of the integral. And integral of 1 over z minus z naught
Is 2 pi I.
is 2 pi I. Which what we just solved.
Yeah.
Okay.
But I don't see the connection between all this. Then we
Maybe
didn't,
it's
we didn't
below.
need to do all this.
What do you say? You cut off.
I'm saying, you see all this work? I don't see why we had to do that.
Yeah, there is no conclusion.
You see, at this point, everything is enough. You see, at this point, we saw this is analytic. It's going to become a 0, right?
Yes.
Oh, this was showing us. This was just showing us that this will be a 0. This becomes a 0. This was just proving it. why it becomes a zero. It's about all this continuity, epsilon, delta to zero. But my argument is, even without that, I can see this is the definition of a derivative. So this function is analytic. And then according to Cauchy's theorem, its integral will be zero.
Yes, your method was shorter.
I don't see why we are doing epsilon, delta, and so many things, but at least it's good to know what the notes are saying. At least I can see that all this was to show that this integral will become a zero. That integral will become a zero. And if that integral becomes a zero, then we have that this integral f of z divided by z minus z naught dz will be equal to the integral f of z naught z minus z naught dz. And given this, if we kick out the whatever you said, because it's a constant, z minus z naught, then this is going to be f of z naught multiplied by 2 pi I, right? So we have that the integral fz divided by z minus z naught dz is going to be f of z naught multiplied by 2 pi I, right?
2 pi I.
So if you divide both sides by 2 pi I, you get 1 divided by 2 pi I integral f of z divided by z minus z naught dz will be equal to f of z naught. And so we have proved the Cauchy integral formula.
How you get 1 over 2 pi I?
I divided both sides by 2 pi I.
Pi I, okay, got it.
Remember, we were all this time, we were trying to verify this theorem.
Yes.
F of z naught equals 1 over 2 pi I contour integral of f of z divided by z minus z naught dz. And there you go. We just verified it. We got it. Yeah.
So we solve it. We will prove it by that we try to find integral of the whole 3 curves of the C, G, and A to B and B to A. And B, B, and A will cancel out. And we have only 2 contours which are equal or equals to the negative. It depends on the direction.
Yeah.
Okay, it's understandable. And after that, we're solving that FZ is getting constant. And we're taking it out. Oh no, it's different notes. It's right here. And we're give me a second. Wait, hold on.
So let's just take it from this point. So this is integral fz dz divided by z minus z naught, right?
Yes.
So integral f of z over z minus z naught dz is the same as the integral f of z minus f of z naught plus f of z naught divided by
z minus z naught.
Z minus z naught dz. You see, these two are the same thing because minus f z naught plus f z naught is nothing.
Okay.
And so this will be the same as we can split the integrals f of z minus f of z naught divided by z minus z naught. And then we have plus integral f of z naught divided by z minus z naught dz, right? At this point, this becomes 0 because it's an analytic function. We can see clearly that this is the definition of a derivative.
Okay, yes, I agree.
So this integral f of z divided by z minus z naught dz equals integral f of z naught divided by z minus z naught dz. But now because we can pull the f of z naught out, this becomes f of z naught integral 1 over z minus z naught, which is the same as 2 pi I, right?
Yes.
So in the end, we have integral f of z divided by z minus z naught equals f of z multiplied by 2 pi I, right?
Mm-hmm.
So if you
Yes.
multiply both sides by 1 over 2 pi I, you multiply both sides, the f of z naught remains on one side alone, right?
Mm-hmm.
And then
Yes.
on the other side, we have 1 over 2 pi I integral f of z divided by z minus z naught. And that is your Cauchy's integral formula.
Okay, I understand. Now it's clear.
Yeah. That's clear, should be clear. Okay, so we proceed. We just proved that formula.
Mm-hmm.
So f of z is analytic in and on the closed contour.
Mm-hmm. It will be 0.
So this is going to be that. That is the Cauchy's integral formula.
Okay.
F of z say is given on every point on C.
Mm-hmm.
Yeah. Okay. Just one moment.
Mm-hmm.
Okay. Okay, so let's proceed. So f of z say is given on every point of C. F of z naught will be equal to 1 over 2 pi I integral f of z over z minus z naught dz. That's Cauchy's integral formula. So by CIF, f of z1.
What were you reading? Sorry, could you?
Sorry.
I mean, I don't see. Oh, okay.
Yeah.
Mm-hmm.
Yeah.
Okay.
So f of z1 is going to be that.
Okay.
Again by Cauchy's
Amazing.
integral formula.
Cauchy integral formula.
So
it was a one man, Cauchy, where's only he, it's only his name figurated everywhere. Cauchy integral, Cauchy Riemann.
I think he is the father of complex analysis. Cauchy and Riemann.
Okay.
Yeah. Riemann was more of a geometry guy.
Okay.
Yeah, I think they did all this together. They came up with all these complicated things.
Cool, I understand.
Okay. So here we have an example. This integral will be equal to 0.
Which integral? What integral?
This integral will be equal to 0 along curve C1. Oh, sorry.
I don't see a cursor.
This, sorry.
Okay.
This integral will be equal to 0 along curve C1. Why?
Okay.
Why do you think that will be the case?
Because it's analytic inside of the curve.
It's going to be analytic there. Along C2, it will also be 0.
C2.
Yeah.
Oh, where is C2? C3. Okay, C2. Yes, of course,
C2 is
because it's
there.
analytic also. Mm-hmm.
But along C3,
It's not analytic because
we have the point
at the
3.
point 3, its analyticity is failed.
Yeah, there is a pole there.
There is a pole at point 3, right?
Yeah.
For the 3.
Yep. So that integral, Cauchy's integral formula, is the one that is going to help us somehow. You see, the formula says that 2 pi I multiplied by
FZ1, function of Z1.
f of, let me just call it Z0.
Okay.
It's going to be the integral f of
F
Z
of Z
divided by
over Z minus Z1.
Z minus
Z0.
Z0
Z0, yes.
dz. Remember, I asked you a question. What happens when we have a pole? What happens when the function is not analytic? The integral will not be 0. And then I asked you, what will the integral become? And then you said, we are going to calculate it.
Yes.
So let's calculate. This integral is going to be 0 because it's analytic. It's also 0 because it's analytic. But it's at this point, it's not 0 because it's not analytic. There is a pole at Z0 equals 3, right?
Yes.
So what will the integral become? So the integral is going to become
Z squared over 2 pi I. We are using this Cauchy integral formula.
Yeah.
So
so this integral will become integral f of Z.
Z squared Z plus 1.
So this will be Z squared divided by Z plus 1
equals
over
2 pi I.
Z minus 3. I'm just writing it so that you can see this is your f of Z. This is the Z0.
Okay.
And you see, this is the same thing. This is the same function.
Okay.
I've just written it differently.
Okay.
Can you see why I did that?
To understand why our 1 over 2 pi I, it's changed to 2 pi I.
So it's going to be equal to 2 pi I,
2 pi I
multiplied
times
by f of 3.
Z f of
right?
3?
Yeah.
Okay, yes.
And what is f of Z? This is f of Z, right?
Yes, right.
So f of 3 is going to be equal to 3
9.
squared, 9. 3 plus 1 is 4. 9 over 4, right? So the integral will be 2 pi I
9
multiplied by 9 over 4, which becomes 9 pi I
9 I over 2.
over 2. There
But I didn't understand why 2 pi I. According to the Cauchy integral formula,
yeah,
it says that f of Z naught equals 1 over 2 pi I.
Yeah. It says f of Z naught equals 1 over 2 pi I, integral f of Z, divided by Z minus Z naught, right?
Z naught.
What if you multiply both sides by 2 pi I? You get 2 pi I f of Z naught equals integral f of Z divided by Z minus Z naught. And that is this.
Okay.
Yeah.
Okay. Got it.
Yeah. Actually, this is a whole new way to me. It's a very new way of integrating. Because in my notes, I do it so differently.
Mm-hmm.
And I guess your lecturer has something good in him. For the first time, he has better notes than mine. I have just loved his way of doing it. Yeah.
Don't be so impressive.
Yeah. Because in my notes, I first calculate what we call a residue.
Uh-huh.
And then after calculating a residue at a simple pole, I take 2 pi I, and then I sum all the residues. But in his case, he's taking 2 pi I, and then just taking the function at that simple pole.
Okay.
Yeah, that's nice. Yeah. Let's see. Let's try doing an example by our
Steven,
own.
can I very quick use restroom?
Yeah, it's okay.
Yeah, thanks. Sorry. I came back.
All right.
Let's do homework, an assignment.
Okay. So they want us to integrate along curve number 4. On curve number 4, we have a pole at -1, right? So Z0, so let me write the formula first. 2 pi I f of Z0. It's going to be the integral, contour integral f of Z divided by Z minus Z0 dz. So on curve 1, Z0 is -1.
Okay,
right?
yes.
So this function, Z squared,
it's not analytic, over Z plus 1
over Z minus 3.
Okay.
Divided by
okay.
Z minus -1. I have written it all over again.
Okay.
And I have written it like that so that you can see your f of Z on top. And then you can see the Z minus Z0 down below there.
Okay.
So to get your answer, you will just need to do 2 pi I multiplied by f of -1. What is f of -1?
It's 1 over -4.
It's 1 over -4. So it's going to be 1 over -4, which is going to be negative pi I over 2.
Yes.
So that will be the
Negative
integral
pi over 2.
around that point.
Okay.
Why did they get pi I?
We forget to use limits. No, it's 1. It's -1. 1 divided to -4. G square, it's 1. 1 over 4. I think it's mistake. He made a, no, he said that the 1 is turning, -1 is turning to 1. I think it was
Why?
his mistake.
That must be his mistake.
Yes, because it's impossible. I mean, like, if it's a -1, it should be -1. -1 minus 3, it will be -4. We're talking about the point where z equals -1, right? Right.
Yeah,
I think it's his mistake.
I think this should be.
Do you see that nobody like didn't, no one says during the class that he made a mistake,
Yeah,
because 100 people just believe him.
yeah. But that's clearly going to be a mistake. That is, he assumed this is 1 minus 3, -2. No.
Yes.
Yeah.
If
So
we have a different function, yes, it's
yeah.
could be true, but we have z plus 1. That means that z equals -1. So okay, pretty clear. Z-plane.
Now what did he draw?
We have, he draw 3 contours, G1, G2, and C. C contour equals integral of G1 and integral of G2. Okay, it's understandable. Because integrals of AB's and AB's primes are gonna cancel out. He doesn't spend time on it.
Okay.
Okay, and this curves and the function of these curves are not analytic. I mean, like, oh, he's explaining the example which he provided. No.
He's just getting the integral. So to find the
Yes,
integral of the whole function at the whole curve, this whole curve, you're going to take the 2 integrals, you add them up, you get your answer.
9 pi over 2 plus negative I pi
This
over
is negative
2.
I pi over 2. So it should be 8 I pi over 2. So the final answer should be 4 I pi. You see, even our answer looks good.
Yeah.
Yeah.
Better than his.
Yeah.
Two pi I f of z. Okay, he's changing the abbreviation. If f prime of z naught equals gf over dz exists, then all higher order derivatives of z naught exist. Why we're talking about derivatives?
Actually, remember we talked about derivatives the other time. We said that if a function is analytic,
Yes.
then
Yes.
all
Yes.
the other derivatives, they are going to exist.
Mm-hmm.
So he changes that. I don't know why. Maybe we will know later.
Okay. So star 2 pi if of z equals integral of closed contour c f of peta theta g of f such that CIF Cauchy integral formula after change of rotation. 2 pi I look at here. He is using the first principle of differentiation. Z plus delta Z minus f of z. I mean, he using this rule because it's derivative.
Mhm.
It means that we can use also the rules of power here in integration.
He must be trying to prove something. He's trying to prove something. So f prime. Oh, he's trying to. Okay, so f is that. F prime is that.
Well, he did get square. Okay, it's f prime, but it's not cubic, but it's integral. Integration of our function. Why it's getting square? Z minus Z not square.
He used the quotient rule.
Quotient rule.
He just did d.
Okay, 1 2 pi I is the same
of fz over z
Divide.
minus z naught. He differentiated this. And remember, this is the same as fz multiplied by z minus z naught to the power of negative 1. So you can differentiate this.
Square.
It
Yes.
becomes 1, right?
Yes.
And then you leave this.
Negative 1. But why it's not
Zero.
negative 1? Why didn't change the sign?
You know, I differentiated the first one and then you add, you keep the first one.
Negative 1.
You keep the first one. For z, and then you have negative 1. Z minus z naught.
Z naught square.
To the power of negative 2.
Negative 2, yes. And it's going down.
So this is the same as 1 over z minus z naught plus f of z minus
okay.
f of z over z minus z naught
square.
Squared.
Where is the minus?
Okay.
Okay, it's just a derivative. It's understandable.
How did he get the square? It doesn't add up.
Yes. And where is also the first part of our?
It's the derivative with respect to z naught, not with respect to z. You know, those are two different things.
Okay.
It's the derivative with respect to z naught, d z naught. So this is the same as f of z multiplied by z minus z naught to the power of negative 1. You differentiate f of z, it's not a function of z naught, it becomes 0. And then you keep that, right? And then you keep the first one, f of z and then you differentiate the second one, which is -1, and then z
Yes.
minus z naught to the power of -2. And then the derivative of this with respect to z naught, it's going to be -1.
Okay.
-1 times -1 is positive. So your final answer becomes f of z divided by z minus z naught squared. That's right.
Okay. Okay.
That's right. And then here he has this f of z is that. So f prime, here he is differentiating with respect to z. So he chooses to write d dz.
Where? Okay.
And then he gets the same result. Same way we did it. And then, so he's just trying to show you that you will always get a derivative.
As much as we can, as we want.
As much as you can. And he gets a general formula for getting it. If you want the nth derivative with respect to z naught, it's going to be n factorial over 2 pi I integral f of z over z minus z naught n plus 1 dz. Yeah.
I hope I understand.
Yeah. So yeah, you know how he got this? He got this by doing first derivative, second derivative, third derivative, fourth derivative, and then he got this pattern. The pattern just came up.
It works only when the f of z is analytic inside and on the contour of S.
Yeah. So here's an example where he wants you to find f prime of this. He wants you to find the first derivative and as well as the second derivative.
Okay.
And it's with respect to z. That is f of z. It's up there. It's analytic. So this integral will be equal to pi I. Why is he talking about f double prime of z naught?
Which one are you talking about?
The example. Okay, so let's do it. So we have the nth derivative with.
Let's use the formula.
Yeah, that's what we want to use. But why is this z? Is it supposed to be z naught?
No, we're taking of the upper of z. But yes, we need to take of z naught. Oh, depends on.
Oh, I see. So, you know, I don't even know what he wants us to find. So he has given us an integral there. So f double prime of z naught equals that. I don't know what he wants us to find. So he has given us that contour integral. The function above there is analytic on C.
So,
And
I lost his idea.
so there is a pole down there. I can see it.
Okay, yeah, because it's not analytic at that point.
Yeah.
But the upper side is analytic. Then we need to use Cauchy integral formula, right?
Yeah. To find that integral.
But we didn't use derivatives in our Cauchy integral formula.
No, we didn't.
And we need to combine Cauchy integral formula and this formula for, I mean, like for how we can find derivatives. Combine into the one.
We already have the formula for finding
derivatives.
The derivatives. It's here. F double prime of Z naught equals that. So let's just use it. Let's use it. Let's do F, the first derivative. The first derivative at 3. It's going to be n equals 1.
3.
So it's going to be 1. You see Z naught is going to be 3, right?
Okay, n factorial is 1.
N factorial is 1. This is 2 pi
I. Integral
f of z
contour C.
It's
z cubic divided to z minus 3 in
to the
cubic.
power of 4.
Why 4? Oh yeah, it's
because
3.
It's n minus 1.
N plus 1. Okay, it's 4. GZ. Okay, and we've got something else. And now he said that it's 3z square, the first derivative of z, but he's derivating by z, by not z naught.
Yeah. We can always find this. I don't know whether Cauchy integrals formula. Did it give us a way of solving this? You know, this pole is order 4.
Yeah.
Did Cauchy integral formula, does it work when the pole is of order 4? I don't think it does. Okay. So let me just bring in my residues. So the residue at z equals 3 is going to be equal to 1 over 2 factorial limit. Z is approaching 3. And then we do a second derivative. No, actually, z is going to be 4. So this is going to be the pole is of order n, so the order is 4. So this is going to be 3 factorial. Z approaches 3. Second derivative, actually that derivative, the z3, and then we have z minus 3 to the power of 4, and then we have f of z, that's the cubic, z minus 3 to the power of 3. So this one goes away, this one comes to that. So we need to find the third derivative. So this will be z to the power of 4 minus 3 z cubic. First derivative will be 4z cubic minus 9 z squared.
Z square.
12z squared minus 18z. So this is the
24z.
This first derivative, second derivative. So that derivative will be 24z
Z
minus
18.
18. And then we let z approach 3.
3.
So if z approaches 3, it's going to be 24 times 3.
72.
72 minus 18.
It's
40.
50, 56, 54.
54.
56. 54.
So it's going to be 54. So that's the limit. And then 54 you divide by 3 factorial. 3 factorial is 6. What is 54 divided by 6? Is it 9?
9, yes.
So the residue is going to be, the residue at that point is going to be 9. And to find the integral, you just do 9 multiplied by 2 pi I. So this integral, this one, this integral will become
times 3.
9 multiplied by 2 pi I. And then the 2 pi i's, they cancel out. So I get f, the first derivative at 3 is simply 9. Did they get 9 anywhere?
Pi I 6, 9.
Problem is we don't know what he's trying to do, because if it's looking for the first derivative of 3, I am getting 9. Okay, so let's leave that. Let's look at this. What is he trying to do again? So there is that problem. He writes this like that. FZ is analytic. That. Then he goes to another problem. Do you know what he's trying to achieve with the examples, or maybe what he is looking for? Because he just writes an example, gets the derivative of that function on its own by itself, and then he multiplies it by pi I. Why he even multiplies by pi I don't know. So I'm lost with his examples because I don't know. At least he could have said what he's trying to do. Maybe he could have written a question. Find this.
No, it should have easy.
Yeah, because we could even do it in our own way. But I have a problem with Cauchy Riemann. I have a problem with Cauchy integral formula. And I want you to think about this. Does Cauchy integral formula work with poles of order n greater than 1? Because going up, if I go up to that formula, where was it? Yeah, here it is. You see, it only, it seems like it's working with, you see, this is z minus z naught, it's power 1, right? That is a simple pole, okay? So the question is, how would we go about it? Can Cauchy integral formula help us when the pole is order greater than 1? What if it's z minus z naught squared? What would happen? Because when you look at the examples that we worked with, look at this example. This was z plus 1. This was a simple pole. This was also a simple pole. What if we had something like z squared over z plus 1 squared, z minus 3 squared? What would happen if they were not simple poles? So that's what I will be thinking about. And it's something good for you to think about as well.
Yes, of course. I'll check. Maybe there's some question about.
Yeah.
Isn't.
Yeah.
Maybe someone asked. We have like a platform where the students can put answers about it. But I'm just checking it, and there is no still any question about integration. They're still talking about analytic functions and some lecture material.
Oh, it means we are ahead.
Yeah.
It means we are ahead.
Yes, we're ahead.
That's good.
Yes.
Yeah. Okay.
Yes, okay. So, Steven, yeah, let's talk about it I don't know. Am I gonna schedule class for tomorrow?
All
But
right.
I don't think so. Yeah, I will. I think I'll schedule it on Thursday.
Yeah.
Yeah, and let's discuss about it on Thursday. I also sent you the last lecture, which was yesterday.
Yeah.
And the residue. I don't know this theorem.
So the
also.
residue theorem, it's the theorem I use to solve complex integrals. It's an alternative.
Mhm.
It's an alternative to Cauchy integral formula.
Mm.
I
Okay,
was,
maybe next time you.
yeah, next time I'm going to teach you the residue theorem, and then you're going to compare it with Cauchy integral formula. Most probably you're going to love it.
Okay.
Yeah.
Okay, so let's do it next time.
Yeah.
I send you last lecture, and yeah, that's it for tomorrow, or for today. Tomorrow, I said.
Yeah.
Yeah, let's meet on Thursday. Okay.
All right. Sure.
Thank you.
Okay.
All right.
All
Have
right.
a good night, and I don't want to waste your time. It's our time is over, and
Yeah. Bye bye.
you gotta go to. You also have your stuff. Thanks. Bye.